Good evening, my dear JEE warriors. Welcome to the Roar series, which is your free series on YouTube in pure English for your entire JEE content. The 11th as well as the 12th standard syllabus. So today we have the 11th standard chapter of momentum and collisions. And those of you who missed any of the previous classes, remember you can definitely find it out in the previous live sections. And last lecture, I had done center of mass and how it moves, right? And today we are going to start off with this new chapter of collisions and momentum. And let me also remind you, you can find all the previous lectures in case you are not able to find it easily in this particular sheet called as the Jungle Book. The link is there in the description box. Open it and you will be able to see all the DPPs, PDF notes, everything for all the subjects, and this will keep on getting updated regularly, right? So that's your Jungle Book, guys. So let's begin right from the basics, right from the scratch, right from zero level. We'll scale it up and take you to the J level. It's a detailed class. It's not exactly a revision. It's not, like a 1 hour, one shot revision or something like that. It's a proper detailed marathon class. All right. So let's begin. And I hope I'm audible and visible. Hi Sanju, Full Beast, Forsven, hi Joseph, Harborine, good evening Harshit, hi Dark, hi Imran. Nice to see you all back onto the channel. Yep, and I hope you have done your regular stuff. And what is your regular stuff that you need to do? Your daily routine. As soon as you come over here, smash the like button. Why? You are telling YouTube that, listen, I like to study for JEE, or else it will keep you distracted by showing you unnecessary content. Also, it is your Guru Dakshina. Number 2, subscribe. Why? Or else you will miss out on all the other updates and notifications and the academic content. And then you will keep searching. What is the channel name I'm searching? I'm not getting. And that's it. And you will not get day-to-day, updates of our classes. And you will only lose track. So let it be a systematic thing where you are attending all our classes regularly. Yeah, this is for 11th, 12th as well as droppers. Rotational motion will be after this. Yeah, rotational motion will be after this. Okay, so we'll do that, don't worry. So let's begin with the lecture. Okay, and let's start with momentum, collisions, impulse, everything. So we'll start off with momentum, we'll slowly go to impulse, then we'll talk about collisions, conservation of momentum, types of collision, and two-dimensional collision, all of this. Okay, hi Vandana, hi Nikhil, glad Sanju I'm audible and visible. Yes, 11th grader can watch this because I'm starting from the basics. So even a dropper student, remember, sometimes you would have forgotten, or a 12th standard student has forgotten. I'm starting from the basics. Now, when I talk about this chapter, usually the kind of questions are, things are hitting each other, or something hit the wall and reflected back, or something is being stopped suddenly. So those kind of things will be happening. And usually you draw a diagram before and after. Just like in work, power, energy chapter, you release something, it comes down with what speed. You throw something with some speed, how high will it go in that circular track? So always there was a before and after situation. Same thing happens in this chapter. Usually most of the problems has a before and after the collision or after the impact kind of diagrams or scenarios, which you have to analyze. Now for this, the first term that we need to know is momentum. So momentum is the effect of mass and velocity together. It's a vector quantity. It's a vector quantity in the direction of motion, in the direction of its motion. If a large rock moves with very high speed, it is said to have huge momentum. Also, even if there is a very small object, but if it is thrown with a very high speed, it can have a large momentum. But a small mass moving with normal speed will not have much momentum. Something which has no speed or no mass will not have any momentum. So that's what momentum is. And the formula for our Momentum goes as follows. So if you have some mass and let's say it is moving with some velocity v, the momentum is also in the same direction. The symbol is p. So that momentum p is nothing but m times of v. That is the formula of momentum. That is the formula of momentum. The SI unit of momentum, is kg. This is kg. This is meters per second. Or you can also use gram. This is centimeters per second. That is also okay. Alternatively, you can also write momentum as, since kinetic energy is momentum square by 2m, therefore 2m multiplied by k is equal to p square. Therefore, momentum can be also written down as root of 2 times of mk. Root of 2 times of mk, where k is nothing but the kinetic energy. What is this k? This k over here stands for the kinetic energy. This is also okay. That is how different formulas of momentum are. I hope till this point everything is clear. I am very good, Vandana, and yeah, I do often take regular classes only, but maybe because we have so many teachers, right? So by the time my turn comes, it takes some time. But yeah. Yeah, there is a crash course planned in the days to come. Definitely, there is a crash course planned. Now, that was your momentum. Now, what happens when momentum changes? And let's talk about it. Say, for example, if momentum changes, now this can happen only via one way as per Newton's second law. That is by application of a force. Without any force, you can't change the momentum, be it the direction or be it the magnitude. So when I say momentum changes, it is either magnitude or basically direction. This can change only when there is a force acting on the body. And who said this? I am not saying this. This is as per Newton's laws of motion. And this amount of the change of momentum, this particular change in the momentum, is given a new terminology, and that is nothing but called as the impulse on the body. It is called as the impulse on the body. How much ever is the change is called as the impulse, and the symbol for impulse is J. Change in momentum, if you remember, change in momentum is going to be delta. Momentum is P, so change means delta P. So that's it. Delta P is nothing but J. This J is an impulse. It is a vector quantity. Unit wise, it will have the same unit as momentum. So unit wise, again, it will be kg meter per second in SI, or in CGS unit, it will be again gram centimeter per second. So any kind of change of momentum which happens because you have applied a force, that is referred to as the impulse acting on the body. Don't worry, we will solve some questions so that you guys get an idea of it. Yeah, all right. And although I never attend the classes, trust me, I attend every single class is recorded. IIT Delhi is going to be mine. I am so glad, Vignesh, you attend all the classes recorded. That shows your dedication and love towards the channel as well. Keep up the spirit, Vignesh, and very soon I will be seeing you on the other side from IIT Delhi. Yeah, stay tuned till the end. Yeah. So Dark Knight, you can see my older classes. It's there on the channel, older playlist. You can just go to the playlist tab. You can see my old classes as well. Okay. Now, if I want to calculate how much this particular impulse is, so let's take an example over here. In fact, we can take more examples only. Let's start by taking a simple example. If a ball of 200 grams moving at let's say 20 meters per second is basically reversed its motion, reversed its motion by a bat with a new speed of 30 meters per second. Question is, find the impulse which acted on the ball. That is the question. Let's try to solve this. Let's visualize it first. So there is a ball of some mass, okay, which is basically 0.2 kg, 200 grams is 0.2 kg. It was moving with 20 meters per second. Now it has been reversed by application of a force by a bat. So it reverses and comes back with 30 meters per second. So in this process, 100% there will be an impulse, and that is what we have to find. Momentum changes if direction changes or magnitude changes. Here magnitude also changed, even the direction also has changed. So 100% there is an impulse. So J will be nothing but, as per definition, it is change of the momentum, which means final minus initial. Now here comes the catch. You choose which direction is positive for you. It's completely up to you which you want to take as positive. I will say maybe right side is positive. Somebody else will say, sir, left side is positive. It's okay. It's just a sign convention. What you do, let's say for example, you take right hand side as positive, which is our usual sign convention. So as per that, my final momentum will be negative because it is towards the left side. So the momentum will be mass, which is 0.2, sorry, it will be first of all negative. Mass is 0.2 kg. Speed is nothing but 30. So that's my final momentum. I hope you understand why I put the minus sign as per the new sign convention. Minus initial. Mass is 0.2. Velocity is in the direction of positivity. So don't have to put any negative sign. So this minus and this minus will just become a bigger minus. 0.2 is common. And then we have 30 plus basically 20. Right? 30 and 20. I can add this because the minus is common in both the places. And this will be minus 2.2 into basically 30 plus 20 is basically 50. Right? The decimal shifts, it will become 2 into 5, which is just going to be minus 10 kg meter per second. Now what does this minus 10 imply? What does this minus 10 imply? This negative sign implies that the impulse is of 10 kg meters per second along negative x axis as chosen, or along the final direction of the motion, our motion, which is towards the left hand side. Is this clear? Magnitude wise it is just 10. This topic has very high weightage. Yes, Nirupanama, expect one question for sure. Up to 2 questions can be asked. Now you will be like, 2 questions, isn't it a small number? But obviously guys, 25 questions are there only. Alright, so if you are having 25 questions and out of that, if there is a chapter which can have 2 questions, obviously it becomes a high weightage to medium weightage chapter. Yes, water lover, we do have 1 year mains program that covers both 11th and 12th standard topics. It is called as the pro batch for 12th standard. So although we say it is for 12th standard, 11th standard classes are covered later on after the 12th standard, before mains obviously, okay, during the course of revision. So that's what we do. Okay, or else another best option is to join the dropper batch, which starts with 11th, 12th simultaneously, but that is usually not recommended for 12th standard students. best is to join the 12th standard batch, which gives priority to 12th. Simultaneously, 11th standard starts immediately after 12. That is called as the pro batch. There is a link in the description box called as admission inquiry form. Fill that form. Our counselor will get in touch with you. They will help you, guide you what you can do the best. It's up to you. After end of the day, it is your decision what you want to do. Okay. So there is an admission inquiry form. Just fill it up. All right. So I hope this problem is very, very clear. Let's go to the next question, guys. Imagine, there is a particle of mass m over here. It is going with a speed of u like this, and it turns and then finally goes with a speed of 2u like this. Question is, find the impulse in this situation. Question is, find the impulse in this particular scenario. Let's try to solve the problem. Now, since in this problem, it's not in one dimension, it's a 2D problem. So I might have to use I cap, J cap. That will be better, I feel. All right. So let me assume this as x-axis, this as my positive y-axis. Okay. As per this sign convention, my impulse vector, which will be final momentum minus initial momentum, which is nothing but the change of the momentum. The final momentum is in the y direction. So it is in the j cap direction. How much is the mass? It is m. How much is the speed? It is 2u. Direction wise, j cap. Did you get it? Why j cap is there? Because it is going in the vertical direction. Minus initial momentum. Mass is m, speed is u. Direction wise, it is going in the x-axis. So it should be I cap direction. So if you notice over here, m and u are basically common, and then I have negative I cap plus 2 j cap. So that is basically your impulse. That is basically your impulse. But somebody might ask you what is the magnitude of the impulse. Then you just put mu over here and the root of minus 1 square plus 2 square. So it will be mu. 2 square is 4, minus 1 square is 1, 1 plus 4 is 5. So mu root 5. So the impulse is basically mu root 5 units. Mu root 5 units. Direction wise, if you ask me, negative I cap means this way. This is negative I cap. So this is minus mu I cap. Mu to j cap. So that will be in the positive direction. So let me do one thing. This is minus mu I cap. Positive to mu j cap. So mu to j cap, it's in this direction. So the net impulse will be basically in this direction. So this is where that impulse will be. If they ask you by any chance what's the angle which it makes with the horizontal line, then you can say, hey, listen, I can just find tan theta, and tan theta will be 2 mu magnitude wise by mu magnitude. So mu cancels, so it will be 2. So theta will be tan inverse of 2 with negative x axis. With the negative x axis, it is making that angle. So you can find that as well. Yeah. Afifa, the class will be 2 to 4 hours, anywhere in between. Got it, Harborine? Okay. Yes. This is clear, everyone? All right, water lover, you got it? Okay. Fine. So I hope now you understood what impulse is. Now, is impulse somehow related to the force? You might be wondering. Is impulse somehow related to the force? And it should be, because if momentum has changed, it's because of the force as per Newton's law, and that change in the momentum is called as impulse. So maybe this change in the momentum, if I can't calculate it directly, somehow it is related to the force. And why not? It should be. So let's come to the topic of impulsive force and impulses. Okay. So as per Newton's second law, as per Newton's laws of motion, our dp by dt, which is the rate of change of momentum, is our net external force. Take that dt on the other side, So dp bar will be nothing but f dt. Okay. Now what I will do is I will integrate both sides. I will integrate both sides like this. Limits, let's say starting from time 1 to time 2. This is also time 1 to time 2. Why have I put the limits? Because obviously it will be for a duration which the force is acting, and during that duration the momentum might keep changing. dp's integration is basically p only, but this will give me, this is not T1 and T2, this will be P1 and P2, sorry, P1 and P2. So this will be nothing but P2 minus P1, final minus initial. This will be equal to, just put F dt as it is. You can't do much over here. Just put from T1 to T2. What is this? This is change of momentum. This is nothing but our change of momentum, or which is the same thing as impulse, So delta P, I can also put or, which is nothing but impulse. Delta P, or basically impulse, is nothing but, so this is our delta P which we got before, is nothing but integration of the force with the time from initial to the final value. That's it, from initial to the final value. So this is something which we should definitely block. So this is how impulse or change in momentum is related to the force. And now it makes sense that, oh, if I apply a large force, therefore the momentum will change by a larger amount. If the time interval is large, obviously it will, if I'm applying the force for a longer time, then also, yes, I can say that the momentum will change by a larger amount. Hence, impulse is also dependent on how much force acts for how much time. Large force acting for a large time changes the momentum by a large amount. So I can say the impulse is more. And we know integration is related to whom, guys? Integration is related to whom? Area, right? So therefore, if somebody gives me a graph of force versus time, and let's say the graph happens to be something like this, okay, and say for example, this is T1, this is T2, this particular area that you are seeing right over here, that area under the graph is this integration. So hence I can also say over here, this is nothing but area under the force versus time graph. This is also correct. Okay guys, everyone till this point absolutely clear about this? This chapter is very similar to work per energy, or rather it is, because there is before and after, number one. Number two, you will see work per energy will be used in this chapter of collisions, especially during the types of collision also. Alright. Now, I have seen many students get confused between impulse and force. Please remember, impulse is not a force. Impulse is a different physical quantity. It is the effect of force with time. A large force for a longer time gives me a good area, which means bigger impulse. So don't confuse between impulse and force. Second thing which I get from this equation is, the unit of impulse can be also written down as Newton into second, because force is in Newton, time is in seconds. So now I can probably go back a little bit over here and I can say, hey, wait a minute, impulse, I can also write it as Newtons into seconds. That is also perfectly fine. Correct? Because it is the effect of force and time. Now, you might have heard about this term called as impulsive force. Okay, sir, I understood force is different, impulse is different. But what the hell is this impulsive force? Force being described as impulsive. It's like the adjective for it. It is describing that word force. What do I mean by that? Let me give you some examples so that you understand it. Say, for example, there is a ball, okay, a ball moving is stopped by catching it. This is first example. Second example, a ball moving is slowed down by a long elastic rubber or band, or basically spring. What is the difference in both of them? This ball which was moving, suddenly it loses its velocity and it stops. Here in this case, the velocity will be large, slowly it will lose its velocity because it's an elastic rubber band or something like that before it finally stops. Here the actions are very fast. In fact, it won't even take so much. It's just probably just going to happen within hardly a fraction of a second. Here it takes a long time before it stops. So tell me, in which scenario, if the ball was the same, speed was the same, impulse will be more? First scenario or second scenario? Where do you think the impulse will be more? Yes. Very good, Nikhil. I think you already mentioned it. You already mentioned it. Thank you, smiling gamer. It will be the same. Initial momentum, mv. Final momentum, 0. So the change of momentum, same. Impulse, same. But our brain is telling, no, impulse is more here. Impulse is less here. No, it is wrong. Impulse is the same. So in fact, both these things have the same impulse. And like, sir, something feels different, sir. So I'll tell you what is different. So here J1 and J2, obviously if I put this as J1, this is J2, both are same, but just like I showed before, impulse is force into time. Imagine force is constant, then I can just write the area's force into the time interval directly. So here on the right hand side, this J2 will be the force in this case into the time interval in the second case, whereas here it will be the force in the first case into time interval in the first case. What happens is this time interval is less, so the force is more. Here the time interval is more, hence it is slow, right? Yeah, time interval is more, hence the force is less. Correct. Everything is fine. Yeah. Here the time taken is less. It stops immediately. You are catching it tuck. Here, that's why the force will be more. Here you are catching it slowly. Spring will absorb that energy slowly. So takes a longer duration. So the force is also very small because it takes longer time to stop. Hence, this force over here is said to be impulsive force. This one is said to be non-impulsive force. It's a relative term. You always compare it with respect to other forces surrounding that body. So the same ball, the same mass being stopped in two different scenarios. I can compare the two scenarios. So the one where the force is large and for a smaller duration and can produce the same impulse is said to be impulsive, whereas the scenario where the force might be acting for a large time to produce that same momentum, means the force is not enough and you need it to be applied for a longer duration. Such a force is said to be non-impulsive force. Graphically, it looks very good actually to visualize it. Impulsive versus non-impulsive. What will be same is the area under the graph. What will be same is the area under the graph, but you will see the shape will be slightly different. Here the force is more, right? So probably you will see no force is there. Suddenly you cast it. It will go like this probably and go like that. Here it will probably go like this for a longer duration before probably it goes down. What will be same is nothing but the area under the graph, which is impulse. Area under the graph will be the same. Is that clear, everyone? The difference between impulsive force versus non-impulsive force? Absolutely. Why is the second example non-impulsive? Because to get that same effect, you need to apply the force for a longer duration. Just imagine you have to stop the train. Imagine you are doing it. Aram se, you are holding the wheels of the train. Let's assume that your hands are made of steel and does not get damaged. If you try to stop the train slowly by holding the wheels, obviously it will run for some few 10-20 kilometers only and then stop. So the force which you applied is small, time taken large, and the momentum changed by the same amount as compared to, imagine the train colliding with another train, thub, or a brick wall, thub, or a rock. Large force, small time, same effect, same change of momentum. So that's when you can compare impulsive and non-impulsive. Got it? So now obvious question is, sir, what do you mean by long? Is it like 1 second, 2 seconds? Like I said, it's a very relative term. It's very subjective. It is not like 1 second means it is impulsive, anything more than 1 second is non-impulsive, nothing like that. There is no, border to it. It's a very, very subjective definition. So, please don't by heart, oh, spring force is non-impulsive, oh, this is impulsive. No, it depends from problem to problem. It depends from problem to problem. Keep that in mind. Yeah. Okay. So, it depends relative. It's like, is this cup hot? This tea cup, is it hot? You'll be like, yes, sir, it is very hot. But then, if you see molten iron or maybe boiling water, you might be like, this cup is not at all hot. Oh, why is this like this? So, it's again very subjective. Getting my point? Okay. So, there is no formal definition of who is impulsive and non-impulsive. It's just a very subjective, relativistic definition or understanding. Let's probably take some examples to get here. Okay. Say for example, a ball of 200 grams moving at 40 meters per second is caught in, caught in 0.1 seconds. Is this going to be impulsive in nature? Imagine this 200 grams ball moving at 40 meters in 1 second and it is caught up within fraction of 1/10 of a second. Definitely. Siva Ganga, please don't spam. You can watch my current electricity class. I have explained it, okay, in detail. Okay. So the question is obviously find the force. So obviously this is an impulsive force. Find the impulsive force by the hand. Find the impulsive force by the hand catching it. Okay, that's the question. Let's try to solve this. So first of all, impulse is nothing but change in momentum, which is also nothing but force multiplied by time, force multiplied by the time, that is what I can say. Now, do I know how much the momentum changed by? Yes, final minus initial. So that is nothing but force into time. Finally, it was at rest. Initially, it was moving with some speed, so minus mv, and force multiplied by the time. But I am more interested in the magnitude of the force, so I'm not interested in the negative signs over here. So I'll put a mod symbol, so that force will be basically mv divided by delta t. What is the mass? The mass is basically 0.2 kg. What is the speed? It's 40 divided by 0.1. Decimal cancels. 2 into 40 will make it basically 80 Newton. So that is the force acting on it. So this is a force that you can expect, which your hand is applying to stop that particular ball. Smiling gamer, I hope, just like your name says, you stay smiling, and I hope you find your new love for gaming probably inside IIT. Trust me, the gaming experience, gaming competitions, hackathons inside IITs and NITs are next level. So I really want that to be your motivation to enter these top-notch colleges. I hope you become a top-notch game developer or whatever maybe your interest is. Yeah. All right. Siva, probably I'll answer your question towards the end. I don't want to break the flow of this chapter. Okay, towards the end you ask me. Towards the end. All right. Now, let's say I give you another question like this. Here, the question is of average force, and this is also a very, very important definition. Sometimes you might be asked to calculate average force during an impact or during some collision, or when there is any kind of change in the momentum. So how do you calculate the average force? See guys, just like since instantaneous force by Newton's law was derivative of the momentum with respect to time, therefore can I not say the average force? Triangular brackets means average. So instead of d, it will be basically delta p by delta t. And what is delta p? It is nothing but the impulse itself. So impulse divided by time gives me basically the average force. So that is the answer. So keep this definition in mind. Average force is impulse by the time interval. As simple as that. So in this problem, this 80 Newton which we have found, is it instantaneous or average? 100% this will be the average force. So this is basically your average force. Maybe sometimes the force was more than 80 also. Sometimes it was maybe 90, 100, but other times it was 70, 60, 40 also. So the average value is 80. So because we have taken a big time interval, which is 0.1 second. Is that clear? Isn't impulse the change in momentum? Yes, definitely it is. That's what I have written down. Impulse is also force into time. So there are two ways of looking at it, and that's why I said unit wise also you can go by either kg meter per second or Newton second. So there were both the ways of writing impulse. Impulse is change in momentum or the effect of force and time, basically area under force time. Both definitions are perfectly fine. Is that okay, Akila Sukumar? Yeah, great. Now coming back to some question again. Let's do this. If the force acting on a body from t is equal to 0 to t is equal to 1 second, or let's say t is equal to 0.5 seconds, is given by F is equal to 4t 0.5 minus t, all right, newtons. Question is, find impulse and the average force. Find the impulse as well as the average force for that duration. Let's understand this. First of all, the force is a function of time. That means it is not a constant. That means 100% it is not a constant. So what do we need to do? When force is not constant, to find the impulse, we have to find basically area under the graph. Area under the graph means integration. So I have to integrate force with time between those limits. That's what will give me impulse. Okay, so let's do that. So as per the definition, the impulse is nothing but integration of force with the time from T1 to T2. Now force is basically 4 comes outside and I will have T into 0.5 minus T dt from 0 to basically 0.5. But I can split up all these terms, expand this. So it will become 4t into 0.5. So 4 multiplied by 0.5, t into dt will just become t dt from 0 to 0.5 minus 4 into t will make it 4 outside t square. Obviously this dt is there from 0 to 0.5. I've just split these terms. This negative sign was there. So t into 0.5 into 4. 4 into 0.5 into t and dt is there. Next term will have 4t, t and dt. 4t, t and dt. Perfect. 4 into 0.5 is 2. T's integration is t square by 2. Limits of the integration 0 to 0.5 minus 4 as it is. T square's integration is t cube by 3, is basically t cube by 3. So just put it over here, 0 to 0.5. Let's see what happens next. Impulse will be this 2 cancels, put 0.5 over here. So 0.5 square minus 0 square minus 4 and 3. So 4 by 3. Okay, put 0.5 over here. 0.5 is basically 1 by 2, 1 by 2 cube. Basically 1 by 2 cube minus 0. Because if you put 0, it will be 0 only. So what is 0.5 square? It is 1 by 2 square, which is 1 by 4 minus 4 by 3. 1 by 2 cube is 1 by 8. So this will cancel. This will become 2. So 1 by 4 minus 1 by 6. Alright. LCM is basically 24. This goes 6 times. This goes 4 times. So this will become 2 by 24, which is 1 by 12 kg meter per second. So that is the impulse. 1 by 12 kg meter per second. Is that clear, everyone? Till this point? Yep. Monish, I'm a mechanical engineer from NIT Nagpur. Yeah, I did my BTech and I did my research from IIT Bombay. Yep. I cleared my JEE in 2005, teaching for more than 12 years. Been there in a software industry, had a small startup back then. Yeah, so that is my basic qualification. All right. Now, going ahead. Yes. Thank God, Sangeet, you're liking the 3-4-year-old classes too, because I put in as much effort before as I'm putting now. It's not like it will reduce. In fact, it will get better only. Yep. Now, that was the first part. What about the average force part? Average force is impulse by the time interval. Impulse is 1 by 12. What is the time interval? It is 0.5 seconds. So 1 by 12, 0.5 is nothing but 1 by 2. So it will become basically 1 by 6. So hence the average force is 1/6 of a Newton. That is the final answer. So that's how you can solve problems of average force or just impulse. Okay. Is it clear, everyone? Shall we go ahead to the next point? Next type of question coming up on your screen. Here it is. Here it is. In this case, there is a nice little graph given. This is force, this is 0, this is time. The graph goes something like this. So this is in seconds, this is in newtons, this is the force which is acting on that body. Question is, find the impulse and average force for, actually these are all in decimal places. This is 0.2, this is 0.4, this is 0.6, this is 0.8 for 0.8 seconds time, for that 0.8 seconds time. Okay, chalo, try to figure this out. This something force time graph we have seen already. Okay, come on, let's see if you can figure this out. Come on guys, don't spam in the chat box or the admin will ban you. Yeah. So in this scenario, force time graph is given. The area under it will definitely give you impulse. So just try to find the area under each part. So let's say for example, you find the area of this particular part. This particular area of that triangle, which is half base, which is 0.4 multiplied by the height, which is basically 5, will be, now 4 by 2 is 2, 2 into 5 is 10, that decimal is there, so this will be basically 1. Similarly, you can also find the area under this particular part, which is half into base. 0.8 to 0.4 is again 0.4 only, height is basically 2 only, so 2 into 0.4, but this area will be negative because it is below. 2 cancels, so it will become negative 0.4. So therefore, our total impulse, which is area under force versus time graph, will be 1 minus 0.4, which is basically 0.6 kg meter per second. That is your impulse. 0.6 kg meter per second. Many people ended up adding it. You forgot that whenever it goes below, it should be considered as negative. Areas work exactly like that. Anything on the top is positive, anything below is negative. So that is a common thing. Even for work displacement, force displacement graph, which gives you work, area under the graph on the top is positive, area below is negative. So keep that in mind. That is a common mistake. That's why deliberately I gave this problem. Is that clear? Everyone, Nikhil, understood? Yep. Yes. Yes, Sangeet. I have doubt in this class is for 12th standard. No, Sangeet. This is not just for 12th. It is for 11th as well as dropper. Remember, this is the 11th chapter in your NCERT textbook. So if you have not studied this chapter back in 11th or you have forgotten this, so this will be like a complete chapter in this particular, lesson, in this particular lecture. Number one. Number two, it's from the basics, so It's for 11th standard students and for 12th as well as dropper students. Okay. Now talking about the average force. The average force is obviously our impulse divided by the time interval. Impulse is 0.6, time interval is 0.8, decimal goes 6 divides by 2 as 3, 8 divides by 2 as 4, so it will be basically 0.75 newtons. So the average force is 0.75 newton. So we solved that also. Is that clear? Everyone? Awesome. So these were the questions on average forces, impulse, finding impulse, all right, and its direction and its momentum. Okay. Now let us come to something called as the thrust force. There are many examples of thrust force. So let me start by giving you some basic examples. Say you have a pipe, and through that pipe, imagine water is gushing out. Imagine there is a Pandu who is holding that particular pipe. Obviously, he will feel somebody is pushing him behind. If you have seen some cartoons like Tom and Jerry, they hold some pipe and maybe Tom is trying to throw some water on Jerry, and the moment the water comes, there is a reaction force and Tom flies off in the backward direction. Or let's say, imagine rain is falling or some liquid is falling on some particular surface. So if the rain is falling with very high speed and big drops of water are falling, so obviously there will be some kind of impact on this particular surface. So there is definitely a force which is acting on this surface due to that moving fluid. Or take the example, Elon Musk, SpaceX company, a nice rocket. It is ejecting out lot of hot gases. Because of that only this rocket goes up. That means on the rocket there is a force in this direction. All these examples, what you see in common, there is a fluid which is ejected or going through something, nozzle or a pipe, and because of that there is a force on the fluid and a reaction on the pipe or that nozzle or that body which is throwing out that fluid. This is called as the thrust force. So when a fluid is ejected or moved through a nozzle, nozzle means opening of the pipe, nozzle or basically that pipe opening, there is an action reaction force on the fluid and basically that nozzle, which is called as this particular action reaction force. This is called as our thrust force. This is basically called as our thrust force. Keep that in mind. Is this concept clear? My dear warriors? Yeah. Chess dude, you should not give the January attempt in 11th standard. I don't think you will meet the age criteria. Okay. Yes, this is exactly rocket propulsion, but in a much simpler way, not in the sense that you are expecting it to be. And that is what is there in our JEE syllabus also. The thrust force concept, not the variable mass concept as such, just the thrust force concept. So how do I find this action reaction force? If one force is action, the other force is basically a reaction force, which is basically called as our thrust force. So for that I need a few things. Number one, what I need is what is the area of cross section. I also need what is the speed of the gas or the liquid or the fluid, and the last thing I need is the density of the gas or the fluid. So area of cross section, density and the speed. If I know these three things, I can find it out. It's not at all difficult. How? I'll tell you. Just imagine a cross section of the fluid, okay, having a width of dx, moving with some speed v, okay, like this. And imagine we have a wall over here. There is this liquid which is falling on this hard surface like this. So till the time it touches the wall, the fluid is moving with the same speed, and within no time, like dt time, it stops. So imagine this cross section moving, and tuck, it hits that wall, stops. And once it stops, it experiences that force, that impulsive force. That is our thrust force. So let's find that out. So definitely there is going to be an action reaction force, so which is our thrust force. So to find that thrust force, first of all, let's talk about how much momentum does this have. There will be a change in momentum in some time. From that, I will find out the thrust force. So the mass of this will be density into the small volume does it have. The volume of it will be, of this cross section, it will have some area. Just think about it. It will have some area of cross section. Let's say that area is A. And the width is dx. So A dx will become the small volume of that section. So multiplying it with density gives me the small chintum into mass. So now, can I find that impulse which is exerted on it? Can I find how much is that impulse which will be exerted on that mass? Yes. It is final minus initial momentum. What is the final momentum? It goes and stops. So 0. What is the initial momentum? It will be mass into the speed. Okay. So basically it is dm into v. But dm itself is rho a dx. So it will be rho a dx into v. Okay. So that is the magnitude of the impulse. So how much shall be the thrust force? It will be impulse divided by the time. How much is that impulse? Rho a dx into v. Time is dt. What is dx by dt? It is velocity. So hence it will be nothing but rho a v square. So that is basically your thrust force. Rho a v square. Like I expected, it is dependent on the density, area and the speed. Rho a v square. Is this absolutely clear? Okay, everyone. So Sangeet, the thing is, those classes were 1 hour duration. These classes are much more than 1.5 hours duration. So I need to also preserve my energy. Is that right? Yeah. Okay. All right. Now, if this much is clear, let's go ahead and solve a question based on this. Coming up on your screen. If a rocket of 2000 kg has to lift off at 5 meters per second square, with an exhaust gas or exhaust fluid whose density is 100 kg per meter cube through a nozzle of 2 meters square. Find its speed. Find its speed. That is the question. Okay. Find its speed through which it will come out. Find its exhaust speed. All right. In rockets, mass change will be big, so how can we ignore it? No, we don't ignore it. Definitely. This is at that instant. So as the mass reduces, because exhaust gases will come out, this 2000 will become 1998, then 1995, etc. So as that mass reduces, the speed of the exhaust gas will also change. So it becomes a variable mass problem. Yeah. So definitely it will change. So in our JEE, you will see all the questions are based on the current mass, not as a mass which changes for a big duration, because rocket propulsion as such is not there, but thrust force concept is there. Is that clear? All right. So now coming back to this particular question, let's try to solve this. First, draw the free body diagram of the rocket which we have. So this is our rocket. Okay. So definitely there will be one force which is there, which is nothing but mg. The thrust force on the rocket will be like this, and the acceleration of the rocket will be upwards of 5 meters per second square. So using Newton's laws of motion, as per Newton's laws of motion, the thrust force upwards minus mg will be m into a. Okay. Thrust force is rho a v square, m mass is 2000, g is basically 10, is equal to mass again 2000 multiplied by acceleration, which is nothing but 5. So basically I will get rho a v square is nothing but 2000 into 5 is basically 10,000 plus, because this will become plus, 2000 into 10 is basically 20,000. So hence this will become basically 30,000, or 30 into 10 to the power 3. Now what about density? Density is 100. Okay. What about area of cross section? I think it is given to be as 2. Speed, I don't know. So rho a v square is this. So 2 zeros cancel, I believe, or okay, 2 zeros cancel, and this 2 by 30, so it will become basically 15. Since 2 zeros cancel, so 1 0 only will remain. So that will be basically v square. So v will be root of 150 meters per second. Slightly more than 12. Slightly more than 12. That should be the answer. Yes, Arborine, root 150. Yeah. Is this absolutely clear, guys, how we found it out? So if this much speed comes out, the rocket will accelerate at 5 meters per second square. But this speed will not remain constant, because the mass will keep on changing. The mass of the rocket will keep on changing. Okay. Won't gravity change? Yes. That is why it is called as rocket science. See, we have neglected so many things in this problem. As it goes up, gravity will change, number 1. Number 2, what will change is, the mass of the rocket. Number 3, because of the rotational effects of the earth, there is something called as Coriolis force, which we have again ignored. Number 4, as the temperature changes, the speed of the gases will change drastically. Okay, it is not so easy. So the engines have to still emit that same energy, and imagine the oxygen has to burn, because as you go up, oxygen will also slowly start reducing. So many things are there. Not just that, the rocket does not just keep on continuously going up as it is. After some time, a big chunk of that engine will come off once it is completely burnt. So that is stage 1. Then there is stage 2. It is just let go. So That is the reason why it is called as rocket science, because it is not a simple equation. It is not a simple thing to solve. You spend years and years just to study it. Yeah. So main thing that you need to know is just this much, nothing more, nothing less. So you will get rocket problems at that current mass, not for that variable mass. Not for that variable mass. It is not there in JEE. Okay, it has been deleted from the JEE syllabus. So don't waste your time on it. Is that okay, Nikhil? Cool. Yeah. Smiling gamer, if you have problem solving questions, I would suggest two things. See more solved examples or the class problems, solve it on your own again. Number two, see those YouTube sessions or your recorded classes where teacher is solving some solved examples or solving some problems basically. Try to replicate the same thing without seeing. Number three after this is doing extremely laddu basic questions, pure conceptual like the short answer questions of H.C. Verma. After that, going to some substitution questions and then going to some average questions and then going to PYQs. That to JEE Mains. Don't even touch JEE Advanced. After this, you can start pushing yourself for more difficult questions, then JEE Advanced PYQs and then more challenging questions also. Got it? So that is a multi-stage thing, just like your rockets have multiple stages. Slowly you build up the concepts and do not spend more time reading theory. Rather spend more time watching and replicating, solving on your own and then practicing before reaching the PYQ stage. Making notes is not so important when it comes to JEE. It's okay if you have 1-2 page notes. More than that, spend more time solving. I hope chainsaw and smiling, that is very, very clear. So that was our first part of the chapter. All right. Now let's go to collisions, momentum and its conservation. There are so many examples related to that. And this is a law which is observed in nature and that is called as the law of conservation of linear momentum. So what does this law say? It says that if the net external force on a system of bodies, is 0, then the total momentum is conserved even if there are internal forces. So this is very important. External force is 0. Then the total momentum is conserved. Even if there are internal forces, it doesn't matter. Also, another important point, mechanical energy may or may not be conserved. Mechanical energy may or may not be conserved. There is no clarity on that. Remember, the conservation of mechanical energy has a different condition only altogether. For that to happen, the work done by non-conservative forces should be 0. Work done should be 0 by non-conservative forces, then mechanical energy is conserved. So if net force is 0 externally, then momentum is conserved. So they have two different laws, two different conditions. Mathematically, I write it down like this. Sigma, that is total net force externally acting on the system, if it is 0, then I will say that your momentum, the total momentum which is there initially will be equal to the total momentum which is there finally. That's all. That is as simple as your law of conservation of momentum. That is your law of conservation of momentum. There are many examples for this, so let's start taking up these examples. Okay, ready with this, everyone? Yeah. Internal forces are not negligible. Internal forces can be huge, but they do not change the total momentum. They can change the individual momentum, but if they increase one body's momentum, they end up decreasing the other body's momentum. They balance it, but they do not change the overall momentum. So that's why internal forces don't even matter for conserving momentum. Let's take some examples. Let's definitely take some examples to solve this. Imagine there is a Pandu and he is holding a gun. And he shoots a bullet, and while he is doing so, he is standing on roller skates on a smooth floor. Now the Pandu plus that gun system has a mass of, let's say, 120 kg. The muzzle velocity, the muzzle speed of the bullet. What is the meaning of muzzle speed? It means the speed of the bullet as it is being shot. Let's say it is nothing but 100 meters per second. Bullet mass is basically just 0.6 kg or 600 gram. Question is, find the recoil velocity. Find something called as the recoil velocity. Why recoil? Because see, Pandu is standing on a roller skate. Everything was at rest. The moment he shoots, by Newton's third law, if there is a force on the bullet, there will be a reaction force on the gun. So that force will push that Pandu behind. That force will push the Pandu behind. Is that clear? Yeah. So now, if I consider our Pandu plus gun plus the bullet system, tell me who are all the external forces. Quickly, think and tell me. Yes, the Pandu's velocity will be the recoil velocity. There are only two forces acting on it, on this entire system. One is their own weight and second is the normal. Nothing else is there in the horizontal direction, so they both will cancel. So the net external force is 0. If you ask me, the force on the bullet, and the reaction on the gun, that will be internal force. It is within that system. Gun, bullet, it is internal, so that won't matter. That won't even matter. So therefore momentum is conserved. So whatever momentum is there initially will be there finally. Initially the entire thing was at rest, so it will be just a big fat 0. That's it. Finally, the bullet has a momentum towards the right. The mass of the bullet is 0.6. The speed of the bullet is basically 100. This is the momentum of the bullet. What about the momentum of the Pandu gun? Pandu and gun is 120. So 120. But they will be moving left side, so negative V. They will be moving towards the left side, so negative V. Is that okay? So now shift that over here. So I will get 120 V is 0.6 into 100, which is just 60. So therefore our speed will be 60 goes with 120 2 times. So it will be 1 by 2, or the speed will be 0.5 meters per second. So this Pandu will go 50 centimeters per second because he has shot it. Is this absolutely clear, everyone? This is the recoil speed. Did you understand why we use plus and minus over here? Plus because the bullet goes towards the right hand side, the Pandu plus the gun go towards the left hand side. That's the reason why we have chosen the signs. Okay, So this is how you solve the questions. Now, if you ask me what is the initial energy, this is a small note over here. This is a small note over here. If you ask me what is the initial energy of the system, the system was not moving only, so it would be 0. If you ask me what is the final energy of the system, well, it will be half mv square plus half mv square. Definitely, it is not 0. So, tell me, is mechanical energy conserved? Tell me, is the mechanical energy conserved once it starts moving? So, that's why it is not 0, because it is in motion. This speed is also there and this speed is also there. So, it will not be 0. So, it is not conserved. Hence, where did that energy come from? Don't get scared. That energy came from chemical energy of explosion. So, the chemical energy is what got converted into kinetic energy of Pandu plus gun and the bullet. All of them got energy from the explosion. That gunpowder would have exploded. From there they have got it. That is why I said, even if momentum is conserved, mechanical energy may not be conserved. Is this absolutely clear, everyone? Clear? Awesomeness. Moving on to the next question coming up on your screen. This is a question in H.C. Verma, and this has been also asked in multiple places in JEE in different ways. So there is a trolley which can slide on that smooth floor, and then there are two Pandus over here, or let's say there is a Pandu of mass 2m who jumps, and then there is a Champa over here of mass m who will jump after Pandu. Champa's mass is m, Pandu's mass is 2m. They are standing on a trolley which is right now at complete rest. What happens first? Pandu jumps from this stationary platform. With a speed u relative to the train. Champa is still standing over there. She has not yet done anything. After looking at Pandu jumping, once the train begins the motion, obviously the train will start its journey like this. After that, Champa decides, okay, even I will jump. So now Champa also jumps, but with the same speed u, again with the relative motion to the particular train. Remember, the train was already moving, so respect to that speed Champa has jumped. So now this train will find a new velocity. I don't know how much will that be. Maybe I assume that velocity to be v2. Maybe here it is v1. The question is, find how much this v2 is. Oh, but there is one more thing which I will need to give, and that is the train's mass. And the train's mass is basically, 2m. Okay, the train, or let's say it is 4m. Let's say it is basically 4m. Okay, so or we can even take a smaller mass so that it will be more fun, because then it will move nicely. Let's say the train's mass is m. Okay, so let's try to solve the question. The trolley is pretty decent, same mass as that of Champa, and Pandu's mass 2m, Champa's mass m. So they jump one after the other. Find the final velocity of the train. Yeah, momentum conservation, of course. So let's start. For the first scenario, what is our system going to be? I think my system will be basically this. This is my system. And let's conserve the momentum. What is the initial momentum versus what is the final momentum? Initial momentum, if you ask me, it is just 0, guys. Initial momentum is obviously 0. Everything was at rest. What is the final momentum? What is our final momentum? When I talk about final momentum, obviously it is the same system that we are talking about over here. So the Pandu has a momentum of 2m into u, 2m into u. The train plus Champa going backwards, so it will be nothing but mass of Champa plus mass of Pandu into this V1. Do you guys agree with this? M plus M into V. But left side, that's why negative. Bring these people over here. So it will become 2m V1 is equal to 2m U. Therefore, V1 will just be U. Coincidentally, this speed of the train plus Champa going backwards is still V1 is equal to U only. So the first part is done, but not yet come to the second part. Now, when Champa jumps with a speed u relative to the train, remember the train is already moving with speed u. The train is already moving with a speed of u, right? So what will be the actual velocity of Champa when she jumps? Can you think and tell me? What's the actual velocity of Champa? Train is moving with u. With respect to the train, she jumps with u. I think it will be u plus u, which will be 2u. Just analyze this. Train is already moving with u. With respect to that further u, so u plus that additional u will make it 2u. Is that making sense to all of you? Is that making sense to all of you? All right. Now this guy moves here. All right. So if I'm going to make only Champa and this platform or the train or the trolley as my system, if that is my new system, think about it over here. Just consider only Champa and the trolley. Don't consider Pandu. Don't consider Pandu. What is the initial momentum and what will be the final momentum? Let's try to write it down. Initial momentum, trolley plus Champa, both are moving like this with that same speed. So it will be m plus m multiplied by v1, but it is going towards the left side. So it is negative. Pandu is no longer a part of the system. Now look at the same system, but after Champa jumping, what will it be equal to? Champa jumping with a speed of 2u. Champa's mass m, speed 2u, but left side, so minus. Trolley's mass m, speed v2, right side, so positive. Is this clear? How we got the signs and the magnitudes? Everybody till this point? So what is there on the left hand side? Just check this out. I'll have minus 2m v1, but v1 is nothing but u only, we just got it, is equal to minus 2m u plus m v2. Oh, minus 2mu, perfect. So guys, we are getting something very interesting over here. So what will I get? M into v2 will be 0. Therefore, v2 will be 0. That means the platform will come to a halt. That means the trolley stops altogether. So Pandu jumped, Champa jumped. The values were in such a way that the trolley came to a halt. If Champa's mass was different, Pandu's mass was different, trolley's mass was different, this answer may not have been 0. Yes. Is this absolutely clear? Isn't it a wonderful problem? Everybody clear till this point? Shall we go ahead to the next? Shall we go ahead to the next question? Okay, let's do this. This is a beautiful question. Basically, what happens, I'll tell you. There is a Pandu carrying a suitcase. Good evening, Abraj. Yes. If Champa jumped first, it might move. Yes, Nikhil. If the order of the events changed in the previous question, then things could have been very, very different. Yeah, maybe it might not come to a rest. Who knows? We can solve that problem also. Same concept, but things might be slightly different. So what happens? This Pandu is jumping with a bag. I don't know what happened. Maybe there was a fire in the building. So he drops down by 5 meters. He just drops down by basically 5 meters. And within that fraction of a second, he realizes that, oh my God, there is a hard surface below. So obviously if he falls down, he will die. So he thinks, he has attended Captain Shreyas sir's class. He knows, I can conserve momentum, I can do something, and I can throw the bag horizontally like this so that I might recoil in this manner. So I will end up landing in this swimming pool. So that way he will be safe. Are you able to visualize this? So after this, what will happen is this Pandu will probably land over here. This might go anywhere. It will hit on somebody's head. I don't care. But at least I am safe right now. So that is the challenge. So the question is, with what speed the bag should be thrown horizontally after dropping for 5 or dropping by 5 meters from rest. That is the question. Okay, I hope you understood what the scenario is like. So let's think what we need to do. Let's assume that the velocity of Pandu is v1, velocity of the bag is v2. So horizontally there was no motion until this point. After this point, slowly the horizontal motion begins, and maybe, the motion will be something like this. But whatever velocity was given here, that velocity will never ever change. This is like horizontal projectile theory, which you have studied before also. This speed will always remain v1, and you have to basically move by 2 meters. Okay. For some amount of time. How much time? I do not know. Okay, that also I don't know. Let's think. If I have to just drop down by 5 meters, this 5 meters using ut plus half at square, what do I get? U is basically 0. So 0. Initial speed is 0. Acceleration is 10. Time, I do not know. So take it on the other side. So 10 is equal to 10t square. Therefore, t is equal to 1 second. So which means if I start from here, if I drop over here at t is equal to 0 seconds, I will be here at t is equal to 1 second. That is one thing which is very clear. If I continue my journey till the entire end point, the total time of fall till the ground will be given by the formula root of 2h by g. What is the total height? 5 plus 40, which is 45. What is g? It is 10. 2 into 45, 90. 90 divided by 10 is 9. So it will be basically 3 seconds. That means you will reach this point at t is equal to 3 seconds. Is this clear? This is 0, this is 1, this is 3. I got some basic preliminary information. That means this journey will be for how much time? That time will be basically 2 seconds. In that 2 seconds, how much will you move? 2 meters with a constant speed. Remember, this will be constant speed v1. Therefore, can I say our 2 meters which was there will be that speed v1 multiplied by the time interval. So 2 is nothing but v1 into time interval, which is also 2 seconds. Therefore, v1 is 1 meter per second. I got v1 as 1 meter per second. Everybody clear till this point? Okay. If I find v1, can I not find v2? Definitely. How? I will conserve the momentum. Conserve the momentum in horizontal direction. Now this is very critical. If you think about it carefully, the net force on it is not 0. How many of you realize net force is not 0? Then you must be worried, how am I conserving the momentum? This is the interesting part, guys. See, even if on a system there is a net external force, don't get worried. In the perpendicular direction, there is no component of it. So along this line, momentum will still be conserved. Momentum is going to be conserved in this direction. There is no problem at all in this perpendicular direction. Is this absolutely clear, my dear students? So that is the reason why I was able to conserve momentum horizontally. Initial momentum before he throws was 0. Nothing was there horizontally, it was vertical motion only. Only after this it split. Only after this we saw that the motion split like this. After throwing the bag, the person's momentum will be negative. It's towards the left side. Mass 40, speed 1. Momentum of the bag positive, mass of the bag 10, speed I do not know. Shift this over here. So 40 will be equal to 10 v2. Therefore, the speed will be nothing but 4 meters per second. So we found it out. The speed with which the bag should be thrown is minimum 4 meters per second, so that he recoils with 1 meter per second, and during his fall for further 2 seconds from here to here, he reaches at least the edge of the pool. Obviously, he will throw with more than 4 so that he will not take any chances, so that he will land over here. Did you understand this question? Yeah, we can include Earth in our system, but then generally if you do that, what will happen? The problem is you will have to consider the huge mass of the Earth and the small velocity of recoil. So we don't do that. Alright, so even though the Earth might not move, the mass is huge, the Earth recoils when you jump, but you don't want to do that. You neglect all those things. So glad, Ramesh. Yeah, beautiful question. Moving on to the next question coming up on your screen. Here it is. A bomb of 6 kg explodes into 3 fragments. 1 kg and 2 kg move with 3 meters per second and 2 meters per second in perpendicular directions. Find the speed of the largest fragment. Find the speed of the largest fragment. This kind of question is also very, very common. Let's try to solve this, guys. Let's try to solve this. Yeah, Nikhil, after this question, we'll solve one more question and then we'll have a small break maybe. Yeah, don't worry. So how do we solve this? First of all, we have a big mass, 6 kg. It is going to be at rest. It is breaking into 3 fragments. 1 kg, 2 kg, 1 kg going at 3 meters per second, 2 kg going at 2 meters per second, both in mutually perpendicular directions. Naturally, the largest fragment of 3 kg, if these two go here, this naturally will go somewhere over here. Remember, like I told before, all our collision momentum problems will always have a before and after scenario. So this was before the explosion. This is obviously after the explosion. This is nothing but after the explosion. Correct. Okay. So let's try to solve the problem because it's a 2-dimensional question. It's not a 1-dimensional question. Let's understand that clearly. This is having 0 momentum. This should also have 0 momentum. That's very, very clear. So the total momentum initially is a big fat 0. Therefore, the total momentum finally will also be 0. Now, because of that, the momentum of 1 plus momentum of 2 kg plus the momentum of 3 kg should be 0. That means the momentum of 3 kg will be negative of momentum of 1 plus momentum of 2. Take these two people over here. So the momentum of 3 kg will be momentum of 1 and 2 together, add them together with a negative sign. Why negative? Wherever their total momentum is, exactly opposite to that 3 kg will go. Exactly opposite to that 3 kg will go. Everyone fine till this point? Everyone fine till this point? Why this minus sign came? Okay, so magnitude wise, the momentum of P3 should be P1 bar plus P2 bar's modulus. Magnitude wise, the momentum of P3 should be P1 bar plus P2 bar's modulus. What is the momentum of the third mass? Assume the speed to be V. It is nothing but 3 into V. What is the momentum of 1 and 2? Well, it's very easy to see. Momentum of 1 kg is mass into velocity, which is 3. Momentum of 2 is nothing but 2 into 2, which is basically 4. Now please remember, P1 is this way, P2 is this way, they are perpendicular to each other. So their vector sum will be root of P1 square plus P2 square. Therefore, 3V will be root of P1 square, that means 3 square plus 4 square, 9 plus 16, which is 25. So this will be 5. Therefore, V will be 5 by 3 meters per second. That is the answer. This speed will be 5 by 3 meters per second. Yeah. Is that clear? Yes. That is the reason we have found out the resultant first, and then we saw it will be magnitude wise same, direction wise obviously it will be opposite. Correct, Charanjit. Clear? All right. Let's do one more question before we hit the break and go on to collisions. Before that, let's do one more amazing question, guys. Coming up on your screen. Now this is combined with projectile motion. Like you see, this was combined with vectors chapter. This was combined with projectile motion, free fall and all of that. Correct? Free fall and all of that. This was relative motion was involved. This was relative to the train. So relative motion chapter was involved. Correct? So you can see all chapters can be combined over here. All the chapters which you have studied before. Okay. So here is the question. I will draw it. That will be better, I feel. This is ground. There is a bird which is thrown with some speed u, making an angle theta with respect to ground. This bird is sleeping, it is not flying on its own, it was a sleeping bird. Somebody took that bird and they have thrown that bird in air with a speed u. So what happens is this bird will travel like this, wants to go here, but when it reaches the top, it realizes, okay, I have been thrown, so it gets angry. So what happens is, this particular bird it lays an egg rather with some force such that it lays an egg, okay, it lays an egg with some force such that it retraces the same path and falls on the person's face who threw that bird in the first place. Because of this, obviously, the bird won't continue this path. The bird will go and land somewhere. The bird is not flapping its wings. It is still, just a passive bird. That means the motion under free fall equations are valid. Otherwise, there will be additional air force and all of that. So in this process, there are two things which we need to find. Where will the bird land? Number one. The speed of recoil of the egg and the bird at the top. Mass of the bird is basically, let's say 2m or let's say 3m. Let's take realistic figures. Mass of that egg alone is m. All this is given to you. So the question is, the egg retraces the same path from the top, from the topmost position. For all this to happen, you have to find what is the speed of recoil of the egg and the bird, and where do you think the bird will land. All these things you have to find out. Yeah, this is like Angry Birds 3, they're like super duper angry. At least the Angry Birds in the games don't throw eggs and smash eggs on our face. Here it is smashing the egg on our face. So let's try to solve this. I don't need all of this. Just remove this for now. Well, this bird had a total mass of 3m plus m. Basically, it was a bird of mass 4m. The bird continues here, so the bird mass is m, and egg mass is m over here. Bird continues over there. Had the bird not laid the egg, the journey would have continued and you would have fallen down at a distance of the range. But now you will not fall at the range, of course. The bird will not fall here. It will fall somewhere much beyond the usual range of the projectile motion. Number one. When you are at the topmost point, just think about it. Before versus afterwards. This is the bird. This is the egg. This is before laying. This is for the bird and the egg together. What would have been the speed at the topmost point? Can you guys quickly chat it, put it up in the chats? Sir, would I solve this question? I can clear JEE mains. Arun Shutan, if you are able to solve this question, definitely you have the aptitude to not just clear mains, but even prepare for JEE Advanced. Because this is a JEE Advanced type of question, which was asked in many previous years. Mains also this has been asked. So definitely you can clear it. Okay, think carefully. At the topmost point, what would the speed be? U cos theta always remains conserved. So it will definitely be U cos theta. Because it is mentioned that the egg retraces the same path from the top, that means if the egg is thrown with the same speed backwards, it will just continue the same journey along the same path. So shouldn't this be U cos theta, everyone? Shouldn't this be U cos theta? Got it, my dear warriors? Yep. Yes, the speed is minimum, Nikhil, but it will be U cos theta. But the question is then, what is the speed of the bird? What is the velocity of the bird? I think I can conserve momentum over here. So, conserve momentum and see what do you exactly get at the topmost point. So initial momentum, bird and egg together, the mass is 4m, speed is U cos theta. Momentum of the egg is negative because it is towards the left side. Mass of the egg is m, speed is U cos theta. Lastly, I have the bird alone whose mass is 3m and the speed I do not know. So basically 3m into Vb will be, take this guy over here, it will be 4mu cos theta plus mu cos theta. 4 plus 1 is 5, so 5mu cos theta is 3m Vb. M and m cancels, so therefore Vb will be 5 by 3 u cos theta. So we found out everything, guys, till this point. If you notice, okay, we have found out everything till this point. So the speed of the bird is 5 by 3 u cos theta. The speed of the egg is u cos theta. All of this is basically at the top. So we have found that out. Speed of recoil of the egg and the bird at the top. We figured it out. Is this first part very, very clear? Everyone? Got it? Question is epic, but we are not done with the question yet. There is one more part which is remaining. Where will the bird land? That part is still remaining. So let's see what do we do for that. I know some of you will be thinking, sir, we got the bird speed, let's apply projectile motion formula and then do it again. So I feel it is little bit crazy to do it that way. Rather, think of it in a much simpler manner. Guys, I told you there is a chapter called Center of Mass, and it is called as a silent killer chapter because suddenly the concept will come from nowhere when you are least expecting it. So here too, the concept of center of mass comes. Even though the bird is going and laying the egg on the top, the center of mass motion is not affected by it because the net external force is still gravitational force. Mind it. So the net external force is the total mass into gravity, which is always the same. The force which the egg is laid is an internal force. Therefore, the motion of center of mass is unaffected. Therefore, the center of mass should definitely lie over here. The center of mass should definitely fall over here. Is it absolutely clear? Is it absolutely clear why the center of mass will continue its journey? And it will fall over here as if nothing has happened. Yes, the egg will fall here, the bird will fall here, that's another story. With this, I can easily solve the question using x center of mass will be nothing but, observe this carefully, I will have mass of the egg into x coordinate of the egg, mass of the egg below, and here mass of the bird, x coordinate of the bird upon mass of the bird. Observe this very carefully now. What happens over here? What is the mass of the egg? It's m1 x1 plus m2 x2 upon m1 plus m2. That's all. Mass of the egg is nothing but m. What is the x coordinate of the egg? When it falls down here, it is basically 0. So into 0. Mass of the egg m. Then mass of the bird 3m. X coordinate of the bird, that's exactly what we have to find. Where does the bird land? We don't know this. So I want to find this out. What is that x coordinate of the bird? Mass of the bird is nothing but 3m. Center of mass, what is the coordinate of it? It is nothing but, this is going to be the range, and the range formula is u square sine 2 theta whole thing divided by g. Perfect. So I will have u square sine 2 theta is equal to 0 plus this and this. So it will be 3m into xb divided by 4m. M cancels. 4 goes on the top, 3 comes below. So x coordinate of the bird will be 4 by 3 u square sine 2 theta divided by g. That's it. 4 by 3 u square sine 2 theta by g. We have found it out. So from the point of projection, it will be at this distance. Isn't it an epic, amazing, like crazy Fodu question? Did you love this? It's one of the best questions, I feel, because so many concepts were involved. Center of mass concept, conservation of momentum, as well as projectile motion. Truly a JEE advanced type of question. It can be a proper passage or probably a multiple correct choice kind of a question. All right. I have 2 questions, Sangi. 2 questions, like I said, in the JEE exam. So the last part of this chapter is collisions, the type of collision and the coefficient of restitution. So we will basically return after the break. Okay, I'll see you guys in a bit. Meanwhile, please like the session. Meanwhile, please like and subscribe. Welcome back. I hope I'm audible and visible to all of you. Do let me know in the chat box quickly. All my warrior pandus. Yep. Awesome. So it's time to start collisions. Before the break, we have done conservation of momentum, impulse, and all of this. Now we will take this particular law to the next level. We'll apply this law in collision problems. Okay, so let's begin. We'll see the different types of collision as well as, the coefficient of restitution concept and oblique collisions. All right, so let's begin. Now, collisions is actually so common that even if you don't see an accident, remember every time around you there is a collision happening. All right, so you might be wondering where. Well, the molecules of the gas are in a constant state of collision. You can't see the gas, but they are always colliding. And the entire thermodynamics chapter, KTG, kinetic theory of gases, it's dependent on how you analyze this collisions at a molecular level. So yes, collisions play a very important role in our day-to-day life, not just accidents or the molecules of a gas, but even how you play carom versus, how you play on a pool table, or, probably there is an asteroid about to hit the earth. So you have to hit another stone or something like that to create an impact such that the asteroid deflects the path. So many places where you can apply the concept of collisions. So we broadly divide collisions into two categories based on the dimensions. If the collision is in one single line or one single dimension, it is called as a head-on collision. Like two cars hitting like this, or there is a ball kept in the front, another ball comes behind and it goes like this. So it's a one-dimensional collision. It happens in one single line. There is no two components or three components. But the moment you get two or three components, maybe some object was here, some object was here, it went like this and went like that. Or some object was here, it hits like this and it goes like this. So that becomes a two-dimensional or three-dimensional problem. That is called as an oblique collision, where the lines of velocities are not collinear. They might be at an angle. They might be offset from each other. They might not be along the same line. Is this difference absolutely clear? The difference between head-on and oblique collisions. Okay. Now, that is not just the only type of collision that we have. Based on the different types of energy being conserved or not, you have three different types of collision. One is called perfectly elastic. Second is or just elastic collision. There is no need of using the word perfectly elastic. This word is not needed. You can just call it as elastic collision. Second is partially inelastic collision. And the third one is complete inelastic collision. Let me give you examples of each and then let me explain what exactly happens. In an elastic collision, basically imagine two protons colliding with each other. Or another example, that rubber ball colliding with an elastic wall. The meaning of the word elastic is that it regains its own shape and size after being deformed. Like for example, your hair. You might comb the hair, but again after some time you realize, oops, it came back. Again you comb, you get irritated, again it comes back. So especially if you have curly hair or seen a person with curly hair, no matter how hard they try to straighten it, again it comes back. So that is like elastic behavior. It tries to regain its original shape and size. Some people have beautiful silky and nice straight hair. So the manner in which you give the shape of the hair, it stays there intact and you are in awe with that hair. So that is an inelastic behavior, where depending on how you deform it, it maintains its shape. Like for example, the dough of maybe when you're making chapatis, rotis, okay, So however you mold it, it maintains that shape. Or clay, if you press it from one side, you give it some shape, it stays there, correct? But a chewing gum, if you pull the chewing gum like this and release, zoop, it will come back. A spring, release it, comes back. So elastic behavior is where it comes back. Inelastic behavior is where it does not come back to its original avatar. Is that making sense? Yep. Even the collision of a photon with an electron, which type of collision is it? Well, that is an inelastic collision. You will see why in modern physics, because what happens is the photon actually gets absorbed inside that electron during atomic collisions, and when something gets absorbed into something, that becomes an inelastic collision. Okay, so photon with an proton or electron is inelastic. Proton proton, electron electron is just elastic collision. Is that okay, Harborine? Okay, in modern physics you will be seeing that in atomic structure. So in case of elastic collision, if you ask me how the graph of energy looks like with the collision duration, this is energy, guys, this is energy with time, you will see the graph looks something like this. It is there initially before the collision, it might get absorbed during the deformation, and then it will again come back to its original level. It basically should come back to its original level, that's all. So there is no loss of kinetic energy, there is no loss of kinetic energy. So the total kinetic energy initially or before the collision is total kinetic energy after the collision. Is this part absolutely clear? So what is this? Initially there was some energy. When it deforms, it might lose some kinetic energy, but it comes back to its original shape and size. So it relieves back the energy stored, and that's why original is equal to the final. So this was my initial kinetic energy, this was my final kinetic energy, it is coming back. Okay, why it is going down? This is during the deformation, during that small millisecond collision. What is happening? Energy is changing for a small time, but it again comes back. Example of inelastic collisions, just partially, will be imagine this a carom coin colliding with each other, or a stone colliding with another stone in air. In this process, what happens is, imagine you throw a stone and you have a friend on friend competition. You have to take a stone, throw it somewhere. Your friend also has to hit the same stone. Imagine, it will be such a fun competition, and those stones collide midair. So they might break into pieces, some sound is heard, some breaking of bonds happens, so there is some energy loss which happens. Some heat might be produced, some stones might become hot, or somebody fires a missile, somebody else fires another missile, doob, the missile explodes, the fragments go everywhere. So that is also inelastic collision, because energy is not conserved. So in such scenarios, what you will notice is that it will have some initial kinetic energy. During the collision there might be some loss, but again it might try to revive back, but it will not come back to its original level. This is final, this is initial, definitely. And if we compare these two levels, clearly there is a difference. So there is nothing but a loss of kinetic energy there is a loss of kinetic energy. I hope this is absolutely clear. What is a inelastic collision? Hi Deepak, welcome aboard. Yeah. Any ideas? Don't worry, we will try to complete as much as syllabus as possible, at least before modern physics, okay, by this month October. Modern physics, you can even watch my older classes, it's not very difficult. This year only I conducted the classes, okay, so you can watch my even older Pathfinder videos, or even the this year's Flash Pro Flash series and all of that. I explained modern physics in a very detailed manner. So waves part, electromagnetic waves, light waves, I will complete it, don't worry. And EMI is left, AC is left, that's it, and light waves, all these things. Ray optics was already done, so we'll do it, don't worry, this month it will be done. Perfectly inelastic collision, this is the worst kind of collision. Imagine something being thrown and it gets stuck to it, okay. So like collision between magnets, collision between magnetic objects, collision between magnets. You take a bar magnet, you take another bar magnet, you throw them and they get stuck to each other and they move together. So when they get stuck to each other and they are not breaking into more fragments or such things, such a collision is said to be perfectly inelastic. So, you know, basically bodies sticking after collision, bodies sticking after colliding with each other, So in such case, what happens is, whatever initial energy is there, it will go down, it will never recover back, and that's it, it continues over here. So that is final, that is your initial, and if you see right over here, so definitely there is a loss, but you can't have a loss more than this. So this is maximum loss of kinetic energy. Maximum loss of kinetic energy happens. This loss can be in the form of heat, sound, light, breaking of bonds, deformation, whatever. But there is some loss. Got it, my dear warriors? Did you now understand the difference, basic difference, examples, graphically, energy-wise, what exactly is happening? Yeah? I hope this is absolutely clear. Concentrate. Don't worry, I'm not going to answer each and every question. Okay. How does my salary make any difference with anything? Whether my salary is 0 rupees, 1 lakh rupees, 1 crore rupees, 10 crores, what does it make a difference? Okay. Concentrate on the class. All right. So now, there is another parameter by which you can immediately tell whether the collision is elastic, inelastic, or perfectly inelastic. Because see, I can tell, hey, listen, the collision, you know, there was some energy loss. But then you'll be like, was it maximum or okayish? If it is maximum, then I will say perfectly. If not, then I will say inelastic. Then how much inelastic was it? Whether it was elastic or not is very vague to, you know, write it in terms of energy like this. So there is a parameter which defines whether it is elastic, whether it is perfectly inelastic, or when it is partially inelastic, how much inelastic behavior it is showing. So let's have a look at it. Nikhil is saying final kinetic energy should be 0. That's wrong. No, final kinetic energy will not be 0 because it depends, may not be 0 rather, because it depends what the momentum was. What if by momentum conservation, final momentum is not coming out to be 0. So the bodies should continue their journey even after sticking to each other. So do not expect final energy to be 0 in perfect inelastic collision. Okay, I hope this is clear. Nikhil, glad you asked that because that is one common mistake which many students end up doing. Do as many mistakes as you want, but only before the exam. So Newton studied the behavior of different collisions and he found out one very interesting thing, that if the objects are colliding, and let's say this can be for 1 dimension or even 2 dimension, doesn't matter. Okay, so what happens is, this is during the collision. This is an intermediate diagram. This is before the collision, and this is after the collision. After the collision. During the collision, when the masses hit, they apply impulsive forces. Why impulsive? Because that force is huge, acts for a small time, and is enough to change the direction or the magnitude of the speed of the other body. So that's the reason why I call it impulsive force, and it acts for a very small time. So can I say that those impulses might act, maybe this body applies on this body applies on this. If J is the impulse on first body, the same impulse is also there on the other body. So can I say that during the collision, the bodies apply equal and opposite impulses on each other. Equal and opposite impulses on each other. This line along which the impulse acts is called as the line of impulse. What is this called? This is called as the line of impulse. Now what happens is, maybe this body had some velocity, let's say u1. This body had some velocity, let's say u2. U is initial, before. Afterwards, maybe this body had some final velocity v1. This had some final velocity v2. What you do is, take the components of each and every velocity along this line. Take the components of each and every velocity along this particular line. Okay, so this will be v1 along that thing. So maybe I can give it v1x. Let's say this is x-axis. Same thing over here. I can say this is v2x. Similarly over here, guys, this is the component here. So it is u2x, and same thing over here. This is u1x. This is along that line of impulse. Let's call it as our x-axis. Let's call it as our x-axis for now. You take all those velocities. That's it. Now, what you do is, just imagine, if you look at before, there is one velocity like this, which is u1x. Another velocity which is like this, okay, which is probably u2x. There is some relative speed between them. Because they might not be equal. So one is moving faster, one is moving slower. So, there might be definitely some relative speed between them. That's the reason why they collide. So you find something called as the relative speed of approach. Relative speed of approach. Relative speed of approach. That is before the collision. And then on the numerator, do the same thing. Afterwards, there will be some velocity after the collision, v1x, and there will be some speed, v2x. They might not be equal, of course. So there is a relative speed after hitting, after approaching, they will separate out. Their speeds will be different in that direction. So there will be relative speed, not velocity, speed of separation. Very, very important. Why speed, not velocity? Because I cannot define division of vectors. So if it is velocity, I can't divide vector 1 by vector 2. So please mind it, it is speed. So the numerator is positive, even the denominator is positive. Both of them are positive. It's not like the ratio is positive, like this is negative, this is negative. No, numerator and denominator individually are positive because they are speeds of relative motion. That is what gives you nothing but something called as coefficient of restitution. Coefficient of restitution, very, very important. And Newton found that for a pair of bodies, it is the same. For a pair of bodies, let's say marble with some another granite, or steel with aluminium, or for wooden box with some another marble box. Okay, so for a pair of bodies, it is basically same no matter what the speeds are. So it's a constant for a pair of bodies. It is an experimental thing. It is dimensionless thing. It is unitless thing. Yeah. How can we know the line of impulse before the collision? So you show the diagram when they are colliding, then you will get to know the line of collision. Now what happens is, if it is a head-on collision, the line of impulse is the same direction of the motion. So you don't have to break your head only, because they will apply forces on each other in the same direction. So that's why for head-on collision, there is no problem. The problem happens for oblique collision, because you have to show when will they hit each other, and then you have to take the components. So it's simpler for head-on. It's little bit tricky for oblique collisions. Is it absolutely clear? When we punch a boxing bag, it is a partially inelastic collision, because your hand does not get stuck in it unless it was made of some material. Maybe somebody had put some gum or some Fevi-stick or something, and your hand got stuck inside of it. Then it will be perfectly inelastic. Otherwise, it is a partially inelastic collision, Sanjay. Okay, it is not elastic because you lose some energy in sound, deformation of the bag and all of that. Is that clear? This is relative speed of separation upon relative speed of approach. That's all you need to do. Okay, and the symbol for that is basically E, small e. Okay, small e. Okay, so for a pair of bodies, it is constant and it is unitless, dimensionless, characterless, hopeless, waste. Okay, unitless, dimensionless, everything. Okay, so coming back, can you guess what would the coefficient of restitution be for a perfectly elastic collision? What would it be for a perfectly elastic collision, guys? Guys, elastic collision, no loss of energy. So whatever speed with which it approaches, it will rebound with the same relative speed after that. So hence, you should probably see the value of E will be 1 in this case. Elastic collision means E will be 1. Worst collision, it sticks after the collision. That means the numerator will be 0. The bodies stick. They are not. It's like Pandu saw Champa after 6 months. Long distance relationship. They ran towards each other. Pandu ran towards Champa. Champa ran towards Pandu. They hugged each other and they kept moving. Elastic? No. Perfectly inelastic? Yes. They moved together. They got stuck to each other. Relative speed of separation, they are not separating. 0 speed of separation. So numerator 0, so E will be also 0, guys. So for perfectly inelastic, E will be basically 0. Imperfect or partially inelastic collision. So obviously E will be less than 1, but it will be more than 0. Absolutely clear, everyone, how this works? Till this point, clear? Harboran, Sanjay, Nikhil, Nitish, Jay, Blessy, long time. All right, full beast, cool. Trending, and ideas, all right. Pooja, okay. Creative minds, Dijendra, Sangi, Vishal. Clear. Okay, perfect. So let's solve some questions based out of this. Say for example, it is given to you that there is a 2 kg mass. It's going with 4 meters per second. There is another 3 kg mass. It is going with 2 meters per second. And they undergo a elastic collision. So obviously after this will have some new speed. This 3 kg will also have some new speed. Question is, what are those new speeds after the collision? What is the new speed after the collision? Let's try to solve this question. It is clearly mentioned it is elastic, so E is 1. Keep that in mind. Okay. Next, can I say momentum is conserved, guys? Can I say momentum is conserved? Momentum conservation can be used. So let's apply momentum conservation and see what do I get. So mass is 2, velocity is 4, positive right side. That's the first body's momentum, plus mass is 3, velocity is again 2 over here. This is the total initial momentum. Final will be 2v1 plus 3v2. Okay. 2 4s are 8, 3 2s are 6, 8 plus 6 is just 14. So 14 is basically 2 times v1 plus 3 times v2. I'll just call it as equation number 1. I'll just label it as equation number 1. Okay, I can't do much after this unless I use some other theory. There are 2 variables, there are 2 unknowns. So obviously I will need 2 equations. Without that, how will I proceed? Okay. So I'll think, because it is given to be an elastic collision, for elastic collision, E is nothing but 1 and it is nothing but separation by approach relative speed. Oh, there is one thing I forgot to mention over here. This relative speed of separation and approach, you do it along the impulse, along the line of impulse, along the line of impulse. In one-dimensional collision, you don't have to worry about it so much. Separation, approach. Separation is afterwards, approach is before. Before, if you see, this is going with 4, this is going with 2, 4 is faster, 2 is slower. What is the relative speed of approach, guys? Can you quickly think and tell me? Approach speed. This is approach relatively. What is the approach speed? Both are in the same. Same means same direction. Use your hands in the same direction. What is happening? Combine the hands together. It is looking like a minus sign. So when it is in the same direction, you subtract the speeds. Big minus small. So 4 minus 2. If they were going in the opposite directions, opposite symbol is this, turn it, it looks like plus. So then you use addition of speeds. That's the trick which I have told you. Okay. Now, what is this over here? V1 and V2. They are also in the same direction. So separation speed, who will be more? V1 or V2? Obviously, after hitting, V2 should be more. So V2 minus V1. Because the directions are same, same means combine the hands together, looks like a minus sign. That's it. So from this, what do I get? 4 minus 2 is 2. So 2 is equal to, 2 comes on the top, is V2 minus V1, or therefore I can just say V2 is V1 plus 2. This is equation 2. Substitute 2 in 1. Substitute 2 in 1. So what will happen is, equation 2 will become 14 is equal to 3 times of V1 plus 3 times of V2. What is V2? V2 is V1 plus 2. Okay, perfect. Let's see what happens now. So 3V1 plus 3V1 is nothing but 6V1. 14 is there over here. 3 2s are 6. 14 minus 6. That is basically 8. 8 is equal to 6V1. Therefore, how much will V1 be? 6 by 2 is 3. 8 by 2 is 4. So V1 will be basically 4 by 3 meters per second. The same thing if I do it for V2 from equation number 2. What do I get? V2 is V1. V1 is 4 by 3 plus 2. 3 2s are 6. So 4 plus 6 by 3, which is 10 by 3 meters per second. That is the value of the other velocity. So we have found V2. We have also found V1. So both the answers are found. Done and dusted. Is that clear, everyone? Yeah. So remember, this was 3 2s are 6, 6 goes on the other side. So 14 minus 6 is 8. So 3v1 and 3v1. Yep. So that is 6v1, 8 by 6, which is 4 by 3. And that is basically 10 by 3. Just check that out. Sachin, I think you made a mistake. Sir, it is 2v1 and not 3v1. Oh, sorry guys. I think while writing down the equations, I made a mistake. So sorry. I will rewrite it. So 14 was there as it is equal to 2 times of v1 plus 3 times of v2. v2 was itself v1. v2 was itself v1 plus 2. Just check this out. Is this correct? 2v1 plus 3 times of v2. v2 is v1 plus 2. v2 is nothing but v1 plus 2. Correct. Now I think it is fine. So therefore, this will become basically equal to 2v1 plus 3v1 is 5 times of v1. 3 2s are 6. 14 minus 6 is basically 8. So therefore, v1 will be 8 by 5 meters per second. Just check this out. Is it 8 by 5 meters per second? Now is it clear? Hi Harshita, thank you so much. Nurture series fan, my god. Thank you for all the love, Pretty Dancy. Thank you so much. Is that fine? Clear? Okay, so v1 is nothing but your 18 by 5. Now over here, this equation if you use, v2 will be v1. v1 is 8 by 5 plus 2. 2 5s are 10. 2 5s are 10 divided by 5. So v2 will be nothing but 18 by 5 meters per second. Great. So we have found out both the answers, v2 as well as v1. 8 by 5 and 18 by 5. Clear, my dear students? That is how you can solve these questions using these concepts. Let's do one more question, guys, coming up on your screen. Here it comes. So what happens over here? There is a 4 kg mass which is moving at 10 meters per second. It hits a 2 kg mass which is kept at rest, and this collision is inelastic in nature, of value of E given to be 0.25. So the question is, find the speeds later on. In fact, you have to find the loss of kinetic energy. You have to find the loss of kinetic energy. That is the question. Yes. If two identical bodies have same, Srinivasala, we'll be doing those special cases in a bit. First, let me do the general cases, then we'll come to the special cases, okay? So let's do this question. You have to find the loss of kinetic energy. Obviously, to find the loss, I will need the new speeds. Without that, how will I even do the problem? V1 and V2 will be needed. This is 4 kg, this is 2 kg. What do I start with? Conserving momentum. Start off with conserving momentum. Initial momentum should be equal to the final momentum. What is initial momentum? Mass into speed. The other guy is at rest, so 0. Mass 4, velocity v1. Other mass 2, velocity v2. So this will become 40 is equal to 4v1 plus 2v2. Divide by 2. It will become 20 is equal to 2v1 plus v2. This is equation number 1. But that is not the story's end. E is also given, so let's do that. So E is given, which is basically separation by approach. Do not forget that. E is 0.25, that means it is 1 by 4. Separation speed, just check that out. Separation speed, V2 and V1. After collision, V2 will be more, just think about it, than V1. So when they are moving in the same direction, relative speed will be this minus this. So it will be nothing but bigger minus smaller. Approach. This guy was at rest. So approach speed will be just directly 10. Nothing great about it. So rearranging the equation, I will basically get 10, 4 goes, this will become 5 times. So 5 is equal to 2 times V2 minus 2 times V1. This is our equation number 2. Now from this, I can see I can add equation 1 and 2. So basically add equation 1 with equation 2. See what do you get. Reason 2V1 and 2V1 will get cancelled. So I'll get 20 plus 5 on the left hand side. 2V1 got cancelled. V2 and 2V2. V2 and 2V2. So this will therefore become 25 is equal to 3V2, or V2 will be 25 by 3 meters per second. Now do the same thing for V1 also. You can find V1 from here, or you can also find it from here. There is no harm. Let's say you use this equation. So 2V1 will be 20 minus V2. So 20 minus 25 by 3. So 20 into 3, 60. 60 minus 25 is 35 by 3. That is 2V1. So V1 will be 35 by 6 meters per second. 35 by 6 meters per second. Just check this out. Correct? So 20 minus V2. V2 is 25 by 3. 20 into 3, 60. 60 minus 25 is 35. So 35 by 3. 2 will go below. So 35 by 6 meters per second. So last part is the loss of kinetic energy. So that will be initial minus our final. Initial is always more. So initial will be half into mass, which is 4 into 10 square, minus, this was initial. Final will be half into mass is 4. V1 is 35 by 6 square minus half into mass 2 kg into 25 by 3 square. That's it. You solve this, you will get the loss of energy in joules. Okay, I think this part you can do it on your own. Is that okay, guys? Everyone till this point? I will use a calculator to find it out because it will involve some bit of calculations, but you can try it out on your own also. Like for example, 35 divided by 6 whole square multiplied by 2. This is coming out to be 68.05. 25 divided by 3 whole square. 2 cancels. This is coming out to be 69.44. And this one, 4 by 2, 2. 10 square is 100. 100 into 2, 200. So 200 minus. So 200 minus 69.44 minus 68.05 comes out to be close enough to 62.51 joules. Close enough to 62.51 joules. This is how you can solve these kind of questions in elastic collision. Okay, guys, shall we go ahead? Yeah, approximately that much. All right, Sachin, you are saying 375 by 6. Just let's see. 375 by 6. Close enough to that. Yes, Sachin, that is around that. Hi, Anbu. Cool. Let's move to the next question, guys, coming up on your screen. Now, this is oblique collision. You have to be a little bit careful. So here, very interesting thing will happen. This is a very interesting question of two-dimensional collision. So what is happening is, there are three identical balls. This ball is coming with some speed, let's say u. These two balls are basically at rest. This ball collides exactly in between. Shuffling happens, momentum is getting transferred, and now this ball, which was already in motion, this comes to a halt and these two start to move. These two basically start to move, obviously with the same speeds because it is symmetric. It is mentioned to us that the coefficient of restitution, the coefficient of I think we'll have to find what is the coefficient of restitution. How much is the value of the coefficient of restitution? And also, maybe we can find out how much is this velocity also. That is the question. See if you are able to visualize this. This ball comes and hits these two balls over here, thup. But as soon as it hits, this ball comes to a halt and these two balls, they go like that. Are you able to visualize this, everyone? It's a beautiful question. Nikhil, maybe more half an hour, 40 minutes, not more than that. So let's see how to solve this. Before, during and after. Okay, since I know what these diagrams are, let's just erase all the unnecessary information. Because it's an oblique collision problem. Remember, oblique collision means two-dimensional, three-dimensional collision. I need to be little bit careful now when I use coefficient of restitution. I have to do it along the line of impulse, meaning the line along which the impulsive forces are. So if you observe carefully during the collision, how do you know which is the line of impulse? Always show during the collision. If you notice carefully, this body applies a force on this body along this line. This same body applies a force on this body along this line. Basically, the forces are along the common normal. The forces are along the common normal. Normal means, see, I have one surface like this, another surface like this. If you draw a normal which is normal to both, that is called as common normal. So the impulse line is always along the common normal. That is a trick which you should remember. That is a trick which you should remember. So I will write that trick over here. The line of impulse is usually the common normal. Is usually the common normal, as simple as that. Oh, so that makes our job easy. Now you either consider this or consider that. Don't consider both, because whatever happens with these two will be happening with these two. One and the same thing. So, you know, for simplicity's sake, let's say we consider this and this. That means this and this. That means this and this. For simplicity's sake, just to solve the problem. So what is happening during the collision? Just observe carefully. Just observe carefully. This is one ball, this is another ball. We are just considering a pair of two bodies, that's all. Before the collision, this body was going right hand side like this. This one was at rest. How much speed was it going? U. Along the direction of impulse, this was the speed. So there will be a component of it. I keep that in mind. Okay. After the collision, this came at rest, this started moving. So this started moving exactly along the line of impulse, and the velocity I do not know. That is what I have to find out. I hope this is absolutely clear. Till this point, everybody understands everything? Okay. But how much is this angle? We can find it out. It's not that difficult to see that when you show these three things like this, see guys, there is a very interesting thing happening. You join the centers. You join the centers like this. It will basically form an equilateral triangle. It will basically form a equilateral triangle whose side length is twice the radius. Radius plus radius, 2 times the radius. So that means the total angle over here, this total angle should be nothing but 60 degrees. That means only this angle will be nothing but 30 degrees. So this component will be u cos 30, which is u root 3 divided by 2. Is this absolutely clear, guys? How we got it? Yeah. The center of mass will be moving in one dimension only. Hi Kamleshwar, hi T, good evening. Are you able to understand? Let's recap. This body collides with this too. So as soon as it touches this on this body will apply a force in this direction along the common normal. That's the line of impulse which I have to consider. I need to resolve all the velocities along that line. After the collision, this body though will go in that direction. It has no other choice. This body was originally going here. So I take the component of u in this direction. So to find the component, I need the angle. So I drew the triangle over here joining the centers, which is an equilateral triangle. Included angle is 60. So half the angle will be 30 degrees. That's how I found out the component that will be needed to solve the problem. So when I write the coefficient of restitution equation, where E will be basically separation by our approach. Separation is just V, guys. Just observe carefully. This guy comes at rest, this guy keeps moving. So separation is just V. Approach will be u root 3 divided by 2. Now the problem is I don't know V in terms of u. If I could do that, my job would have been done. No issues. I have an idea for that. Let's conserve momentum. Let's conserve momentum because you have not yet conserved it. So conserve momentum, but I have 2 dimensions. So how about conserving it in horizontal dimension? So if that's the case, I just need the velocity in this direction and in this direction, which is how much, guys? Just tell me. This will be obviously 30 degrees. So this will be V cos 30. Same, I would need this also, which is again V cos 30. So our initial momentum will be just mu. The other 2 masses are at rest. So that's why 0. After that, this mass comes to rest. So 0 for that, plus this mass m, but V cos 30. But there are 2 such masses, so into 2. That's all. So from this, what am I getting? Cancels. U is equal to 2 times V cos 30 is root 3 by 2. 2 cancels. So V is U divided by root 3. V is U divided by root 3 is what I am getting. So substitute that V as U by root 3. What will happen? You will notice U is there here, U is there here, root 3 is there here, this root 3 is there here, that 2 will go on the top, 2 cancels. So I will get the value of E as U cancels, it will just become 2 by 3. That is the final answer. 2 by 3, 0.667, that means it is an inelastic collision. It is an inelastic collision. Is it absolutely clear how to solve this 2-dimensional problem? Absolutely everyone clear about this? How about we do one more 2-dimensional problem? A very interesting one. Okay, so basically find relation between the angles of incidence and reflection for an inelastic surface. For an inelastic surface, that is the question. As you can see, this is an inelastic surface. Think of a carom coin hitting the border of the carom board, or a pool table's ball hitting the corner or some edge. So it hits, rebounds. What is the relation between them? Your whole life will be a lie if you thought that, I is equal to R, because that's what we think. Angle of incidence is angle of reflection. That is true for light, but this is a particle, that too carrying mass, so that too inelastic collision. So I don't think it is going to be equal. I don't think it is going to be equal. In fact, that will open up your eyes and minds, and you will realize that you were thinking about it in the completely wrong way. So let's find out what is the relation between this and this angle in terms of the in terms of the coefficient of restitution. Okay, so think about it, guys. So when the collision exactly happens, meaning the ball is touching the surface, when the ball is touching the surface, the common normal will be basically this. So this is how the impulses will act. This is how the impulses will act. There will be no force in the horizontal direction, which means this is our line of impulse. This is our line of impulse. So whatever we do, we should do along this line. So this velocity will have a component here downwards like this, obviously. So the original velocity was like this and final velocity was like this. Take the components of each one of them. So take the component like this. Because this was u and this angle would have been I, this would be u cos I. Why is this angle I? Obviously, two parallel lines. If this is I, this will also be I. So that's why it is u cos I. Same thing you can do over here. This would be V and there will be a component along that line of impulse. This angle will be R. So this will be V cos R. So using coefficient of restitution formula, E will be nothing but separation by approach. Separation is separation, what is it? This surface with respect to this ball is separating with V cos R speed. V cos R. The surface is not moving. Approach speed is just the ball's velocity in the line of impulse, which is just u cos I. Did you get it? The surface is not moving, the ball is approaching the surface with that speed and rebounding from the surface, reflecting from the surface with V cos R speed. Okay, this is one set of equation. Let's keep it aside. Let's also simultaneously conserve momentum. Conserve, but in which direction? Conserve momentum. Which direction do you think we should be conserving? Obviously, in the horizontal, not in vertical, because there is a force on it in the vertical. Horizontally, there is no force. Mind that. No external force in the horizontal direction in x-axis. So the momentum will be conserved only along x-axis. Only along x-axis. So naturally, you should see what is the velocity in this direction, which will be u sin I. And same thing over here, velocity in this direction will be v sin I. Why? Because, sin R. V sin R. If this is cos, this is sin. If this is cos, that is sin. So conserve the momentum and see what do we get. In the x direction, it will be m u sin I. M u sin I. Here it will be m v sin R. these both will be obviously equal. M and M will cancel. So U sine I will be equal to V sine R. We can do one more thing. How about writing what is V by U? That will be better. How will be V by U written? V is here, U is here. V is here, U is here. Cancelled. So sine of I, sine of R over here. Why did I write V by U? Because V by U is right over here. So substitute that. V by U is basically sine of I by sine of R, and the remaining terms as it is, cos of R and cos of I. This is equal to E. Therefore, E will be equal to sine I by cos I, that is nothing but tan of I. Sine R by cos R, that is nothing but tan of R. That's it. This is a very important result. In fact, remember this. Restitution coefficient is tan of I by tan of R. Very similar to Snell's law, but it is not Snell's law. In light, this is refractive index. This is angle of incidence, angle of refraction. This is angle of reflection, mind it. Number 3, this is tan. Here in Snell's law, it was sine. But same but different. Same but different. I hope you can see that. So very important result. Now this shows that I won't be equal to R for normal collisions because E will not be 1. In elastic collision, E will not be 1. In fact, E is less than 1. That means, since usually E is less than 1, so therefore tan of I is less than tan of R. Therefore, reflection angle is more than R. So if it comes at 30 degrees, maybe it will go at 40 degrees. So reflection angle is slightly more than the angle of incidence. So that is something which you should keep in mind in our day-to-day collisions. Isn't it amazing, guys? Thank you, Kamleshwar IT. All right, clear, Herborine, Nikhil, awesome. Beautiful question. So we have done quite a few questions on this coefficient of restitution concept, elastic collision, inelastic collision, 2D collision. Even this was a question on 2-dimensional collision. Now it's time that we take some special cases and see what happens in each case. Special cases of elastic collision. If masses are equal, then the velocities are interchanged. That is very simple to understand. Imagine you have a mass m like this, equal masses. This is before, this is afterwards. So if this guy had 5 meters per second speed, this guy was moving at 2 meters per second speed, you will see after the collision, this guy will go at 2 meters per second, this guy will go at 5 meters per second. Not just that, imagine some other directions. Let's say this guy was going at 3 meters per second. This guy was coming like this at 4 meters per second, opposite. After the collision, you will see this mass going at 4 meters per second and this mass going at 3 meters per second. So this guy gets this velocity and this guy gets this velocity. The velocities get interchanged only when the masses are equal, mm. If it is 3 kg, 5 kg, no. 3 kg, 3.5 kg, no. If it is not elastic collision, no. Even if it is 2 kg and 2 kg, it won't work. Only for elastic collisions. Keep that in mind. Okay. Next, special case. If one mass is huge, one mass is at rest, then what happens? Let's have a look at that scenario also. Imagine a very big mass and a very teeny mini mass, and this guy happens to be at rest before this guy comes and hits with some speed. What happens after the collision? After the collision, you will see The small mass hardly had any momentum, it will hardly apply any impulsive force. It's like, imagine I am running, some Pandu is running, some person is running and goes and hits a big rock in front. What will happen? Will the rock move? Obviously nothing will happen. You'll see some small vibration, so it will still be approximately at rest. This guy, because it is elastic, approach speed should be the separation speed, so it should be u. Relative speed of approach is u, relative speed of separation should also be u. Exactly. Yeah, like action reaction when masses are same. Nikhil, yeah, you can think of it like that, or you can think for the previous thing as if the ghost entered over here. It's like two twins. Two masses are equal, that means they are twins. Both the twins had ghosts in them. Both the twins had ghosts in them. This had a ghost of 5, this had a ghost of 2 meters per second. So when these two twins were going like this, the ghost went into each other twins' bodies. There is no way you can differentiate. So that's what happened. That's what just basically happened. So this ghost went into this. So that's why this guy got 5. And this 2 meters per second went into the first guy's mass. Okay. So that was the first one. This is the second one. So here the speed will get reversed. The other mass, heavier mass, very heavy mass will still remain at rest. When will this work? When it is much, much larger. Example, 1000 kg, 1 kg. 5000 kg, 3 kg. But 20 kg and 5 kg, it will not work. 20 and 5 are comparable. Don't apply it then. It should be very, very heavy. Then the next scenario. Imagine there is a very heavy mass and it is moving with some speed u. There is a small teeny mini mass, it is at rest. It's like there is a big rock, asteroid, and it collides with another small stone. Then what will happen? That big rock which is there, it will hardly feel anything, it will still continue with the same speed of u. It will be unaffected. But you know what this small m will do? This will move with how much speed, can you guess? Look over here. What is the speed of approach? This guy is at rest, this guy is coming with u. So separation should also be u. So if you are already moving one mass with u, this guy should move with 2u, so that 2u minus u will make the relative speed as u. So that's why this lighter mass will move with double the velocity. Lighter mass will move with double the velocity. Clear? Hi Janvi, welcome to the channel. And I'm glad you found it at least couple of months before your JEE Mains examination. And I hope that you watch all the previous lectures as well as the lectures forthcoming, okay, in the next couple of days, where we complete all our major syllabus and the revision begins with the mock tests and lot of questions practice. Okay, so stay tuned on the channel for all the updates, guys. And if you have forgotten to subscribe to the channel now, as well as like the video so that YouTube understands that you are interested in studies. And the way the algorithm works is it keeps you away from the distractions. Correct? Okay. So that was the third scenario. Is there a fourth scenario? Yes, there is, for oblique collision, and that too for elastic case. Oblique collision for elastic case, there is a very interesting thing which happens. So it goes something like this. Okay, so this is elastic and oblique collision. Not just that, between equal masses, very, very important. If the masses are not same, this property will not hold true. With one of them at rest initially. One of them is at rest initially. So very interesting thing happens. No. Why does the second mass need to be big? That is not the condition. I mean, it's not other way around, Nikhil. You got me wrong. When the other mass is big, then the smaller mass's speed is 2u. Only then this will work, because only when this is huge. Imagine a Volvo bus, a big truck colliding with a cycle fellow. So the Volvo bus, the truck fellow will not be affected at all. He will continue moving. That small fellow will move with double the speed. We are not interested in finding the mass comparison. Rather, we are saying if we know one is huge mass, one is small mass, then from that information, I can find the speeds. That is what I am trying to say. Is that clear? We are trying to find the speeds based on the masses being very, very different. One is very huge, one is very small. If they are comparable, one is 3 kg, one is 5 kg, then what to do? You have no other option but to use this. See this? How we did this problem? 4 kg and 2 kg. We cannot say, sir, this mass is very huge, this mass is very small. No, I can't say that. Here, I have to go via equations. So we can avoid all this trouble if I know one is like, this is 40 kg, this is 2 grams. Oh, then I know the answer. Right? Otherwise, we have to do all these nonsense. Now, what happens in this case is these velocities become perpendicular. So then the velocities are perpendicular after collision. You will be like, sir, how the hell did you get this? It's very simple. I'll tell you what. Let's conserve the momentum and see what happens. Conserve the momentum and see what happens. But I will write the conservation of momentum principle in vector form. So observe this carefully. Initial momentum will be mu bar, rest, that means 0. Final momentum is mv1 bar. It's in I cap, j cap, k cap, like that. So plus mv2 bar. So conserving the momentum, what do I get? Mm cancels. So therefore, u bar is basically v1 bar plus v2 bar. Okay, let's keep that over there. Next concept, since it is elastic collision, E is equal to 1. So initial kinetic energy is equal to final kinetic energy. That's what I will say. So initial kinetic energy is equal to final kinetic energy. What's the initial kinetic energy? It's half mu square. I know you might be wondering, sir, why are you not taking relative speeds and all of that? So there is a trick which I am using. You will see it why in next couple of minutes. Half mu square is initial kinetic energy is equal to final kinetic energy. Half m v1 square plus half m v2 square. M by 2 will cancel, and what I am left with is just u square is equal to v1 square plus v2 square. Now look at this equation. From this, what do you guess this is? It's a vector addition of two vectors and you get the resultant. So you have v1 vector and probably you have v2 vector like this, and the result of this is this. So basically, you know, this is v1 bar, this is v2 bar, and this is u bar. That is what this tells. But from this, what do you see? This looks like Pythagoras theorem. This looks like Pythagoras theorem. So the diagram shouldn't be like this. Rather, the diagram should be something like this. This is v1, this is v2, and this is u. Then it makes sense. So this is the correct diagram. So this is u bar, this is v1 bar, which is perpendicular to v2 bar. Hence proved. Therefore v1 perpendicular to v2. So it's a beautiful derivation of proving how it comes out to be perpendicular. Super cool. Loved this derivation. It's an amazing method. So that's why you should explore everything throughout the chapter. You never know how you might use this concept in some question somehow. You never know that. Correct? So these were some important properties. So whenever you see a question like this, directly you can mark the answer. This property, this property, this property, you can directly mark this. So oblique collisions we have already done. So no need of these slides. Yes, this is done. So that comes to the end of this particular chapter of momentum and collisions. We have done center of mass. Now, do you want me to do rotation first or do you want me to do, EMI? I think we should do rotation first. We'll do the concept of torque, moment of inertia and all of that, and then we'll go to EMI very quickly. Okay, so be ready for rotation, guys. That will be better, and then we'll do EMI, and then we'll do other chapters, AC, all of that. Cool? Chalo. Have a great time. God bless you all. Take care. Hasta la vista. Captain Shreyas signing off. And do not forget to like the video, subscribe, talk about this channel to your friends, and in the comments, I want this term collided. And if you have to ask me anything, please put it up. Take care, guys.